Hello, everyone. My name is Raul Castaneda. In this new video, I'm going to present my dissertation to obtain the PhD in electrical engineering for the University of Memphis. Before to start, I would like to say thanks, Dr. Douglas, for all the support that you gave to me. Let's start by the outline of the presentation first. I want to start by the motivation, later the background and rationale, the research topics, the summary of paper in Congress, and finally the innovations and the conclusions. So let's start by the motivations. So this thesis proposal is related to the technique digital holographic microscopy. So I would like to start with a short description of what is important in DHM. And the answer is because DHM allows to retrieve information of biological and non-biological samples. So DHM is considered a labor-free technique, which means it's not necessary to stain the samples in order to retrieve information. So DHM enabled the study of microsize in material of life science. So in other words, you can study biological and non-biological samples. Besides, DHM enables the recovery of samples complex field, so which means that you can obtain, you can retrieve information of amplitude and phase, both of them at the same time. DHM has a relevant feature that is that you can obtain further measurements through the spatial coordinates, axial and laterals, and at the same time, you can retrieve at the time. So allowing 3D profiling and tracking. So you can obtain 3D tracking of samples. DHM is considered an out-of-focus technique. So you can obtain information at different planes because DHM allows to retrieve the information of the planes numerically. So it's not necessary to focus the sample with mechanical systems. A relevant feature of a specific architecture of digital holographic microscopy called off-axis allows single-shot measurements. So single-shot measurements means that you can retrieve information of the sample with just one register. So this is relevant because you can obtain information in real time of samples. So why is relevant DHM? DHM is relevant because it's used in several applications, in several fields of science, for instance, in biomedical applications or material science applications. In biomedical applications, and you can obtain live cell imaging, cell morphology, cell proliferations, disease and diagnosis, screening, cancer pathology, drug discovery. In the world of material science, DHM has application, for instance, to detect inspection, measurements, surface topography characterization, and structure team. So let's start with the background, a short background about digital holography microscopy. So DHM is considered a hybrid imaging strategy, basically because DHM is composed by two stages. The first stage is the optical recording of the hologram, and the second stage is the numerical reconstruction, right? So for the recording, an optical setup is necessary. For instance, a Mach-Zehnder interferometer. The interferometer is composed by different optical elements like laser, mirrors, beam splitter, a digital camera, microscope objective, and tube lens. These two elements compose the optical imaging system. So the light that is provided by a laser is split in two beams. the reference beam and the object beams. The reference beam is, by simplicity, a plane wave. And the object beam is the convolution between the magnification of the imaging system and the pupil of the microscope objective. So the sensor records the interference pattern between these two beams, the reference and the object beam. This interference pattern is called the hologram. So like the camera records the intensity of the interference pattern, you can represent the hologram as the modulus square of the object and the reference beam. So now the next question is, why do you record the hologram? And you record the hologram because you want to retrieve the information of the sample. And the information of the sample is encoded in the hologram. So it's necessary the next step, the numerical reconstruction. However, before to explain the reconstruction, I want to explain the different architectures as the hologram can be recorded. So basically, there are three different architectures as the hologram can be recorded. These architectures depends of the angle between the reference and the object beam. So if we compute the Fourier transform of the hologram, there are three terms: the DC term, the less one term, and the plus one term. They are the diffraction terms, right? So when these three diffraction terms overlapping between them, so the architecture is called inline. Now, if you start to move the angle between the object and the reference beam, you can obtain a configuration when they are overlapping between the plus one and the less one term with the DC term, but not between them, right? And finally, when the 3D fraction terms are located in such a way that there is not overlapping between them, so the hologram is recorded in off-axis architecture, right? These are the three main ways you can record a hologram. So why is this important? This is important because depends of the architecture to record the hologram, you can use different algorithms to obtain the numerical reconstruction. For instance, in the line and the slightly off axis, the holograms are based in the principle of phase shifting. And for off-axis architecture, the algorithms to obtain the numerical reconstruction are based in the compensation. So in this dissertation, almost the 85% is in off-axis architecture. So for this reason, I want to explain the process to obtain the numerical reconstruction. So the first step to reconstruct the object in off-axis architecture is create a spatial filter. The spatial filter basically consists to delete the DC and the less one term of the Fourier transform. It's like you obtain, you create a hologram filter. Okay, so now, if after the spatial filter, the next stage consists in multiply the hologram filter by a numerical replica of the digital reference beam. It is called the compensation step. And finally, if the hologram is recorded at image plane, which means that the camera is located in the bifocal plane of the tube lens, is enough to compute the inverse Fourier transform to obtain the numerical reconstruction, which means retrieve the complex object information, in the case, obtain the amplitude and phase information of the sample, right? So, well, now, if the hologram is recorded in line or slightly off-axis architecture, that is not possible to implement the spatial filter. Why? Because in a line and slightly off-axis, they are overlapping between the plus one and the less one term with the DC term, right? So in these cases, it's necessary to implement phase shifting strategies. So phase shifting techniques are implemented for the couple, the undesirable DC and the less one order. They are different approach. And the common technique used consists in register 3 or 4 holograms. And with the hologram that you record with a well-known phase shift between them, it's possible to retrieve the phase information of the sample. Okay, so let's start with the research. Okay, so from this moment, I will start to present the main research elaborated during my PhD. So the first work consists in a new strategy to obtain the numerical reconstruction from 2 images. It means to record holograms. So which one is the motivation? So the motivation for this work born because the conventional algorithms implemented in phase shifting strategies need at least 3 holograms. And also, in order to provide a reliable phase distribution, it's necessary to know to have accurate knowledge of the phase shift between the 3 or 4 recorded holograms. So the question that we are planted here is, will it be possible to obtain a blind strategic method that implement 2 holograms? When I said blind strategy, I want to say that this is not necessary having knowledge about the phase shift between the holograms recorded, right? So let me explain the fundamentals of this work. So Dr. Douglas noted that the hologram that is possible to read in, that is possible to write the hologram like a linear combination of 2 terms. The first term related with the DC term and the other term related with the +1 and the -1 diffraction term. So also we notice that in this linear combination appears a term that is the phase shifting between the 2 recorded holograms, mean the angle, the difference between the angles used to record the hologram. So which one is the issue? The issue is that when in the numerical reconstruction, the phase shift value used is the true value, is the right value. So there are not a remaining term in the Fourier transform of the D0. However, when the value used is the wrong value, I mean, with the phase shift is the wrong value, so it starts to appear like a remaining term from the +1 term, right? So if we use the right value, so it's possible to create a spatial filter because they are at the couple of the plus and +1 term with the DC term, right? So we define a const function, J, that predict a minimum value of the phase shifting implement for the numerical reconstruction, right? So the const function quantify the residual or in the estimated Fourier transform in the component D0. So we can normalize in this image these different values. So this is the value of the const function. So when the value is true, when the phase shifting is the true value, so the value of the const function is almost 0. Whereas when the angle is different, so the value of the const function is start to increase, right? So, okay, this is the flow chart of the proposed method. First, the algorithm needs at input 2 holograms, H1 and H2. So later, we compute the Fourier transform of the hologram, create a random value as the seeds of the algorithm. These seeds are 2 random values for the phase shifting. Okay, so the algorithm start to compute the the const function, right, until obtain the lower value possible. So when the lower value possible is obtained, start the process of the spatial filter and compensation to retrieve the phase information of the sample. In order to validate the proposed method, we compare two strategies or proposed method with two images and a previous work presented by Dr. Douglas where it is necessary implement three images, which mean three holograms, right? So the main contribution of this work is the reduction from three to just two holograms to retrieve phase information in phase shifting holography, of course. Furthermore, there is not necessary a previous knowledge about the phase shifting between the two record holograms. Remember that this is a blind method, right? So in this figure, we compare the outcomes obtained using a start target. These are the 3D phase profile from a start target. In order to create a quantitative comparison, we create two profiles in two different zones, R1 and R2. And they are the profile using two images, the red line, and using three images, the blue line. So it's possible to notice that the phase that we are obtaining with the two implementation is almost the same, right? So a summary, the proposed blind phase shift method is based on the correct modulation of the hologram spectrum. It's suitable for arbitrary unequal phase shift values between two holograms. The method applied for a slightly off-axis DHM system. The proposed method is robust in noise condition and is computationally efficient. At least we reduce in 50% the computational time. Our simulated experimental results show that the proposed approach provides accurate and quantitative phase images. The main contribution of this work has been presented in Imagine Applied Optics Congress in 2020, and also was presented in Applied, and also we have a paper in Applied Optics. Okay, so the second work in the PhD was the implementation of a new algorithm for retrieving phase information free of aberration in digital holographic microscopy for off-axis architecture. So what is the motivation? So the motivation is because some cases, the conventional algorithms don't allow to obtain phase information free of aberrations, or some cases demand high computational time. So the global idea behind this work is the implementation of a const function in order to minimize the const function to obtain phase information free of aberrations. It's important to remember that the main idea behind digital holographic microscopy is retrieve phase information, right? So if the phase information that we obtain after the numerical reconstruction contains fake terms, fake phase values, this involves phase quantification images. So this entails phase information of the sample, right? So in this image, we can notice two phase reconstruction. The image of the left is a reconstruction where there are aberrations. They are aberrations because these terms are fake values for the phase, right? And in the image of the right, we have the ideal scenario. We have the ideal case that is a reconstruction where there is not aberrations, right? So the issue in the numerical reconstruction of axis hologram is the compensation. The compensation is the key to obtain accurate phase information in digital holographic microscopy. So let me explain in detail the compensation step. I said before that the compensation entails multiply a replica of the digital reference beam by the inverse Fourier transform of the hologram filter, right? So the replica of the digital reference beam is easy to compute. Easy because it depends on different terms: the wavelength, the index pixel position, the size of the digital camera, the pixel size, right? But there are two terms that are not trivials: theta x and theta y. Theta x and theta y are the angles that are used to record the hologram between the reference beam and the object beam, right? So the other terms, they are a straightforward way to compute, but theta x and theta y definitely not. So the only parameters to be estimated in the reference way, sorry, are the interference angles. And these values are related with the position of the maximum peak value in the +1 term. So for this reason, these angles can be computed because they are related with the pixel position of the maximum value of the +1 term and the pixel position of the maximum value of the DC term. So we can use these two equations in order to compute theta x and theta y. However, there are a problem. Before to talk of the problem, if the correct values of theta x and theta y are obtained, so it's possible to retrieve the phase information free of any aberration, right? At least aberration that you can obtain in the compensation step, right? Now, the problem is that in the ideal case, the maximum value in the +1 term must be located in an integer pixel position, right? However, this is not the real case. Experimentally, this condition may not always be satisfied due to discrimination of the digital camera, right? So the most common experimental scenario is that the maximum peak of the +1 term does not accurately represent an interference angle, and this is precisely the problem, and this is the reason why the conventional methods fail. So in this image, we can memorize the values of Umax and Vmax. This is the optimal reconstruction, and this is the not optimal reconstruction. So the problem is a huge problem because let's compare this number. In generalize, we can talk that some cases it's just necessary 0.5 difference between the pixels to obtain the optimal reconstruction and the non-optimal reconstruction. Definitely, this is a problem. Of course, there are different strategies to compute in automatic way the reference way. Some of these approaches are based in centroid-based algorithms. Other strategies are based in nested for loops. So in whatever of the two cases, the general or the global idea is to create like a grid and start to look for the best numerical reconstruction. For instance, Trujillo demonstrate that the best reconstruction phase image, which is the one that does not have phase perturbation and has the smallest number of phase jumps. So in these cases, this is the best reconstruction. So we take advantage of this situation to implement a const function. So we implement the const function in order to track the numerical, to track that for the best reconstruction, we obtain the minimum value possible of the const function, right? So let me explain the const function. So in the const function, we have two terms. The first term is the multiplication of the number of pixels, right? X and Y axis. And the second term is a summation of all pixels after a binarization process. So what is the secret? The secret is the following. Let me explain. So when the reconstruction is not the optimal, there are dark pixels. Trujillo just demonstrate that in a previous work, right? So after the binarization, you will obtain pixels that become in dark. They are dark pixels. So if you start the summation of all those pixels, this summation, the number will be smaller. This summation, the value of this summation always will be smaller than the summation in the case where there are not dark pixels, right? So if this summation where the reconstruction is the optimal after the binarization, of course, the summation after the binarization will be a higher number than in these cases. So this subtraction must be 0 or close to 0 for the case that we are working with the optimal reconstruction, which entails, of course, the correct values of U mass and V mass, right? So this is the block diagram of the proposed algorithm. And the whole approach is composed of 4 stages. The first stage is the input parameters, the hologram, the wavelength, the pixel size. The second stage is the spatial filter. Later, let's start the compensation. It's necessary, of course, to define the const function and start the initial values of U mass and V max. Start the minimization process, and the algorithm start to run until obtain the minimum value of the const function. So when the minimum value of the const function is obtained, we catch the values of U mass and V max, create the reference wave, obtain the reconstruction of the phase free of aberration, of course. So here we provide a quantitative analysis of the comparison between our proposed method and other two method based in nested loops and century-based algorithm for 3 different samples: Phaeus subtarget, Drosophila melanogaster flight, and glioblastoma cells. So these are the dimensions of the samples: 1024 by 1024 or 2048 by 2048. So this is the values of U mass and V max. We can notice that the difference is in the ordinal decimals of pixels. The accuracy always is, we obtain the higher value in the accuracy. And an important feature of our proposed method is the processing time. So in nested loop, for instance, for this kind of images is almost 1 minute. We just spent 1.6 seconds. And these other numbers definitely say that the proposed method that we create is faster than at least nested loop. It's much more faster than nested loops, faster than the method based in centroid algorithm. This is the summary. We propose an automatic method for reconstruct phase images recorded by an off-axis digital holographic microscopy system operating in telecentral regime. The proposed method only requires 2 input parameters and, of course, the hologram. The hallmark of the proposed approach is the high accuracy in the estimation of the parameters of the digital reference wave. The proposed method performs 40 times faster than the automatic approach based on nested loops, approximately 2.3 times faster than the century-based algorithm. Experimental results show that the proposed approach provides quantitative phase images without phase perturbation. And the main conclusion for this work has been presented in the Imagine and Applied Optics Congress in 2021. The paper Fast Iterative Automatic Reconstruction Method was published in Applied Optics also in 2021. Okay, so it's time to talk about the third work elaborated during the PhD. So in the previous work, I introduced an automatic algorithm to retrieve the phase information of holograms that has been recorded in image plane. So image plane means that the camera is located on the bifocal plane of the tube lens, right? But what happens if the hologram is recording a configuration that is not image plane, which means the camera is not located in the bifocal plane of the tube lens of the sample, is not located at the object plane, okay? So in this configuration, it's necessary to create to elaborate an in-focus step, right? So a relevant hallmark of DHM is the capability of recovering information from multiple focal planes through a single shot recording hologram, because numerically it's possible to obtain the information at different propagation distance, right? So what is the issue? The issue is that you can record a hologram that is out of focus. Why the hologram could be out of focus? The hologram could be out of focus basically for two reasons. Reason number one, the sensor is located at different distance of the image plane. They are at C distance, or maybe because the object is not located in at the focal plane of the microscope objective, right? So, of course, there are conventional strategies to obtain in focus reconstruction for autofocus hologram. However, the conventional methods do not provide a means for finding the best focal plane and at the same time eliminate aberrations in the phase reconstruction, of course. So, well, other thing that could happen if you are familiarized with digital holography is that some cases you don't have information about the propagation distance used to record the hologram. So this is like the motivation. The motivation is try to create or to obtain a algorithm that can obtain reconstruction in focus, aberration-free for holograms that has been recorded in out of focus, right? So one solution is start to create the reconstruction to different propagation distance, right? However, how many manual reconstructions should one evaluate to find the correct propagation distance? Of course, this is not like the bad solution. So in this order two ideas, we think to take advantage of the sharpness metrics. Sharpness metrics are functions that quantify the grade of focusing on an image to determine the best in focus plane, right? Of course, there are several sharpness metrics. Some of those sharpness metrics are the integrated amplitude modulus, the Tamuria coefficient, the grid variance, normalized variance, energy of Laplacian. So the first task in this research was, okay, which one is the best sharpness metric for our interests? And we take advantage that for a pure phase object, a pure phase object should look transparent when the object is focused for amplitude reconstruction. So we use a target, and we start to retrieve to obtain the reconstruction, the amplitude reconstruction for different propagation distance. We notice that the Tamuria coefficient presents a well-defined global minimum. So we say, okay, this is the cost function that we need to use to obtain the in-focus plane. So after that, after obtaining the in-focus plane, we perform the compensation. For the compensation, we use exactly the same cost function that I defined in the research number 2 of this dissertation. This is the flowchart of the proposed method. There are like 3 main stages. In the step 1 is the define the input parameters. the holograms, the wavelength, the pixel size. The step number 2 is determine the focus propagation distance. So create a spatial filter, define the Tamura coefficient like the cons function, create, of course, the minimization, and start to run the algorithm to perform the minimization of the Tamura of the cons function until obtain the minimum value. Of course, the minimum value correspond to the propagation distance, so the in focus distance, right? So the last step is the phase compensation of the interference angle. So this minimization is exactly the same that I introduced before, but there are here a new element to define is the propagation distance that the algorithm find in the step number 2. So there are some of the outcomes that we obtain. These are red blood cells. The algorithm find that the propagation distance was 50 micrometers. And this is check cells for these samples. We don't have any information about the propagation distance, and the algorithm find the correct propagation to obtain the in-focus reconstruction. In order to perform like a comparison between the proposed method and the conventional strategies to obtain in-focus reconstruction, we compare the proposed method with nested loops for 2 different samples, a phase user target and a start target. These are the image size in 2048 by 2048 for the phase, for the use of target. And for the start target, the image size was 1024 by 1034. So you can write that the Tamura coefficient is almost the same. In the nested loops, we did like a switch between to define propagation distance, like the limits, right? Like boundaries to run the nested loops, right? So the in-focus plane is almost the same. However, there are a huge difference in the time to perform the autofocus and the phase reconstruction. So these are the time for the autofocusing, these are the time for the full compensation, and these are the total time. You can write the difference 182 seconds for nested loops versus 10 seconds using the proposed method. So also it's important to remark that the accuracy for the phase was better using the proposed method. So they are like a summary of this work. We propose an automatic method for reconstruct phase images, aberration-free for autofocus hologram. The proposed method only required 2 input parameters. The hardware of the proposed approach is the synergical combination of the minimization algorithms to find the best focus plane and generate the best compensation. The proposed method runs 20 times faster than automatic approach based on nested loops. Experimental results show that the proposed approach provides quantitative phase images without phase perturbation. And at the moment to present my dissertation, we was reading a scientific paper to be published, but the paper right now has been published in Optis letter. Okay,